The first part of concept 50 was up yesterday online if you looked at that video. So this is going to be concept 50 and we'll just put continued. Yes, so third period and seventh period we did numbers 1 through 5 and then I added some extra ones in there at the end. Yep. The first period class is 1 day ahead right now. So the first period class we did concept 51 today. We'll do concept 51 next class in this class. That'll be on Thursday. Remember, next tomorrow you have your field trip. All right. So we did 1 through 5 yesterday. Then I did a few extra examples along the way. I'm going to start by calling today's number 6, even though it might not be number 6. But if
no, we went to number 6.
But I added that one. I just want to make sure we're clear. If you look in the notes, I call this next one we're going to do number 6. So I'm going to call this number 6, even though it might be like number 8 or 9 in your notes, just so when you're looking at the notes on that line, you're able to refer to this. Okay? You can call it whatever you want, really. It doesn't matter. Okay, so we're doing the second half of concept 50. We did the first half of concept 50 yesterday. Okay, that's what I posted on that. I need to watch that yesterday. All right, so let's take a quick look at number 6. Number 6 asks us the cube root of negative 64 y to the 6th. The cube root of negative 64 y to the 6th. Now, what I'm going to do is this. Today I'm going to do this in the beginning the long way, which is a little bit annoying, but I want to show you the long way so you understand the shortcut. Because there's an easy shortcut to do here. And it's sometimes tough to understand if you don't go through the method. So let's go through the methodology first. So, what I'm going to notice is this. I have a cube root of a number, negative 64. What number goes into 64 3 times and it's the same number? 4. Good, George. Pick it up on these again. 4 times 4 is 16, times another 4 is 64. So the cube root of this 64 part can be easily expressed as just negative 4 because it's negative 64. So what I want to start is thinking about it like this. In my mind, I'm thinking about it like this. Because I can do that. Remember, my rules of radicals is that if I ever have a product under the radical, or if my radicand is ever a product, I can break that up into 2 different parts. And now, as Jordan just mentioned, this is just negative 4. So that part is the easy part. But how do I do the cube root of y to the 6th? It seems like it's very complicated. Again, I'm going to do it the long way now, but in a minute I'll show you the shortcut. But if I didn't know what to do here, what could I do? What's one option? What can I convert to? If I want to find the cube root of y to the 6th, but I don't really know what to do right now. Let's make believe I don't know what to do, which, I mean, I know what to do, but I haven't shown you guys the rule yet. What can I convert this to? What can I make it look like? Instead of as a radical, what did we do with the last one? A fractional exponent. Very good. So tell me, what would this be as a fractional exponent, Marcus? Very good. Remember, again, the index is really the denominator. The power is really the numerator. But what's 6 over 3?
2. No.
Just 2 over 1, or just simply 2. So that's my answer right there, actually, it turns out. Turns out that negative 4y squared is my answer. Now, I don't want to have to convert to rational form every time. It's a lot of work. It's not needed. We can pick up on something. What can we pick up on here? What could we have just done from this beginning part here that would have the same effect on the answer?
You could have like devote like 3y and then like another 3y, make it 6.
We could have
that'll be like 3.
2 sets of 3 y's,
Yeah.
thus y squared. Very good. So that's awesome. What he just noticed. He said, well, I could write it like this. That's one way of thinking about it, right? Isn't there already 6 y's across? And then this cube root of y cubed is just y. And this cube root is just going to be a y. And y times y is really y squared. That's one way of doing it, absolutely. Every time that'll work, yep. And that we're going to keep that in mind for the next thing. So just keep that in the back of your head. What's another thing I could have done to determine that it was just a 2 as my exponent? Yeah, just divide them. So like, see this 6 and this 3 here? What's 6 divided by 3 as we showed here? 2. So you could always take the power and divide it by the index. That always works. But the question becomes this. What happens if it's a number like 7? Is 7 divisible by 3? No, it's not. It's not an integer value. And if I want to see everything in radicals, we're going to talk in a minute how we can do this without that. We're going to use what you just said. Okay? So let's look at the next example for this one. So the next example here, let's say we've got, I'm going to jump around in the notes here. I'm going to jump around. Let's say we've got the fourth root. I'm going to call this 7, even though it's not, sorry. What if we got the fourth root of 16 x cubed y to the 8th? Fourth root of 16 x cubed y to the 8th. Look at the numerical part first, the 16. What number times itself 4 times gives you 16? 2. Because 2 times 2 is 4, times another 2 is 8, times another 2 is 16. By the way, this is one of the rare examples where you can switch up your exponent and your base. What's 4 squared? This is an example, this is a rare example. 4 squared is 16, isn't it? And didn't we just say 2 to the 4th is also 16? It doesn't always happen. It usually doesn't happen. It's very rare that this happens, but notice when you switch them, they're still the same, actually. These both happen to be 16, right? It's very rare that that happens. Just one of those examples. Because if you try 3 squared and 9 to the 3rd, it doesn't work that way. Okay, try it sometime. Or, sorry, if you try 3 squared and then you try 2 to the 3rd, what's 3 squared?
9.
What's 2 to the 3rd, though? Are those equal? So it doesn't always work. This is just one of those examples. I don't want you to think that that's always going to work, just going to happen to you. Okay? But it's one of those examples that you happen to get the same number. So the fourth root of 16, we break it up into like that. Okay, we start by thinking of it that way, and as we said, the fourth root of 16 is 2, so that part's the easy part. Now, I cannot just simply divide this 3 by 4, because 3 is not divisible by 4 anymore, right? But 8 is divisible by 4, right? What's 8 divided by 4? 2. So what I should do with this is the following. I should probably just break this one up so that I see something like this now. And the reason I'm doing this, I'm breaking up anything that is a perfect fourth. So this can be reduced, as we said. 8 divided by 4 is just 2. So this becomes 2 on the outside times the fourth root of x cubed times just simply y squared. Where does the y squared come from again? The 8 and the 4 go in and they become 2. Very good. Again, this number, the power, divided by this quantity, the index, become 2. So that's going to be our rule that we're going to use. But this only works if the number is divisible by the index. Like here, this 3 was not divisible, right? So what I end up doing is writing my answer like this. Okay, and that's a time symbol. You don't need the time symbol there, but I'm going to put it there just to be safe. Okay, so I take everything that can be rooted, or fourth rooted in this case. 16 can be fourth rooted as 2. Y to the 8th could be fourth rooted as y squared. But x to the 3rd, that cannot be fourth rooted. So I leave it alone. Okay, if I'm taking an SAT or a test like that, what's another way I can express this again? How can I express that last term instead of that way?
Put x over 3 over 4.
Well done. Good job there. Okay, I can write it like that as well. Again, I can take this quantity here and think of this as 3 over 4. I can't divide those, so I can technically write it as 3/4. Technically, I can write it as 3/4. Okay? Let's do another example. So for the next example, we're at 8 now. Let's try the fourth root of m to the 4th over n to the 4th. What makes this problem difficult for most students? Not you guys, but for other students. What might make this difficult? Different variables. What else? The fraction. Yeah, different variables in the fraction. But what can we do? What do we know? Did you get 1 over 2? Okay, but explain to me though, Rosie, what are you really doing? You're breaking this up into 2 separate parts, right?
Yeah.
So what Rosie's saying is, well, why don't we just write it like this? Which is absolutely what you want to do here. Okay, you want to think of that radical. as going into both of them. You don't have to write it down that way if you don't want to. Just write the answer, it's fine. I don't mind. And clearly our answer is just going to be m over n squared. Because again, if I take this 4 divided by 4, I get a 1 here really. The 1 I don't care about writing though. And then if I take this 8 divided by that 4, I get the 2 right there. So you can go from the first step straight to the third step. I don't mind that at all. But that's what I want you to be thinking about. Okay, so don't let it throw you off just because you see that there's a quotient. Okay, just because you see that there's some sort of fraction in there. There's no difference on the problem whatsoever. Still though, aren't these are very nice examples, aren't they? They happen to work. Happen to be both divisible here. Let's go to an example now where it's a little bit different than that. What if we had let's say we have the third root of negative 27 x to the 7th y to the 3rd. Okay, x to the 7th y to the 3rd. So, right away, what do you notice? Y. Good. Right away, what number goes into negative 27 3 times and it's the same number? It's negative 3. Negative 3 by negative 3 is 9. By another negative 3 is back to negative 27. So yes, this is a perfect cube, so that part's going to be easy. But here is where it's going to get a little bit tricky, right? I can't do the 7 divided by 3, right? Because of the fact that it's not an integer value you want to bring out front. But if I do it like this, what can I break this up into so that one of them happens to be divisible by 3? How can I break up what you see circled so that one part of it is divisible by 3 and the other part is not divisible by 3? Think about your rules. How do I get x to the 7th? It might be x to the 4th times x to the 3rd, right? Is that x to the 7th? Or x to the 5th times x to the 2nd. Isn't that x to the 7th? Find a combination of those that the exponent happens to have a number that's divisible by 3. Very good. So what Jordan is saying is let's break this up in x6 and x to the 1. Because isn't that really x to the 7th still? And now x to the 6. Can't that come out in front because isn't that divisible by 3 now?
Yeah.
So what he's doing is he's making the problem easier on himself. Well done, sir. So break that up. Let's leave the rest alone for a minute. Okay, so right away again, break up whatever cannot be divisible by 3 or whatever the index is. This 3 is divisible by this 3, so I leave that alone. But the 7 here is not. So now I have this 6 and a 1. And the 6 is divisible by 3. It is divisible by 3. So I want to think in group now. In your mind, you don't have to do this on paper. I'm going to write it. You don't have to write this stuff. If you want to just do it in your head. I'm going to group this by things that can be broken up and things that can't be broken up. So I'm going to say, well, the 27 can surely be broken up. We said that already. The x to the 6 can be broken up. And the y to the 3rd can be broken up. What can't be broken up, or what can't be reduced? That x, right, by itself. So over here, I'm going to put just the cube root of x left by itself. Okay, so whatever can be reduced and whatever cannot be reduced. This is what I want you to be thinking about in your head. If you want to write it down, you can. It might help, especially for your notes. But when you're taking your quiz and stuff, if you want to go from this line right here to whatever we're going to get as an answer, that's no problem at all. So now the cube root of negative 27 is? Negative 3. Be careful again, negative 3. Because negative 3 by negative 3 by negative 3 gives me negative 27. Okay, continue. We have a question?
Yeah.
Yes, go ahead.
How come when, like, dividing the exponent, then you get 2x2, and then you can't, like, add the both of the x's?
No, so right here, that's a good question. When you take this 6 divided by this 3, you're going to get x squared, right? And then the y is going to be 3 divided by 3, which is just a y. This x squared is outside the radical now, isn't it? Where is this x? Remember, inside and outside, they don't correlate to one another. So then at the end, just simply put the cube root of x at the end of it. And these are all multiplying. I'm not going to put a time symbol. You don't need it there. You could have a time symbol right here. Okay, see that time symbol I just inserted? You can have it there, but you don't need it. And you're not going to see it when you have choices in the SAT. So I don't want to put that time symbol there. Okay, again, whatever was able to break down, you put on the outside. Whatever was left over, you leave left over. What's that?
I can use like
Yes, so another way of writing this, absolutely, Jose. Another way of writing this is negative 3 x squared y x to the 1/3. But you would never write it this way because then you could actually combine these two now, and you would write it as a fraction. So this would actually become, it's going to be 1/3 and 6/3 is 7/3. That's what that would turn out to be, believe it or not. If you wrote it in rational exponent form, you would never really leave these two as separate things. You would add the exponents, and 2 is really 6/3. 6/3 and 1/3 would give you that 7/3 there. Okay? But again, on your SAT, when they leave them in the choices, a lot of the time they leave it looking like that. Okay? A lot of the time they leave it in radical form. And on your homework tonight, what I wrote on the back was simplify and leave your answer in radical form. So your answer should look something like this. You're not going to convert it back to this way. Okay? Let's look at an example that's not given like this, though. Let's look at an example that's given a little bit differently. So what if we're given an example that looks like 27 p to the 4th. This is example, what are we at, guys? 9? 10?
No, this is 9.
Okay, one or the other. So what if we're given 27 p to the 4th, q to the 13th, no, let's say 14th, q to the 14th, all to the 1/3 power. Okay, all to the 1/3 power. Now, we can start by distributing the 1/3 to everything and get all our rational exponents. But what if this problem said, give your answer in radical form? Or what if all the multiple choices had all the radicals? Clearly, it's not going to help me to distribute the 1/3 now, right? It might be a little more difficult to do that. So let's start by rewriting this to start in radical form. What does this look like in radical form?
3 radical 2 4
Good, and let's use our terms right though. I don't want to say 3 radical because it sounds, the way you just said that, I would write this. 3 times the square root of something, which is not what we're doing. What are we doing again? Thank you. Very good. The third root of this whole thing. All to the what power, really? Yeah, it's really all to the 1 power. You don't need that one there, and I don't recommend you have to write it. I'm just showing you so you can see that, okay? Again, all to the 1 power. Now, at this point in time, I want to break up my P and my Q into things that are divisible by 3 again. So, 27 is fine. I don't have a problem with that at all. That's clearly divisible by, or that's clearly a perfect cube. We just did that one, that was 3. What about P to the 4th? What should I break that into?
P3, P1,
Why P to the 3rd and P to the 1?
because
Which is divisible by 3?
P3.
Good. So on this side, let's put P to the 3rd, and on this side, let's just put a P to the 1, or just P by itself. Because still, it's the same problem. Go back up and look and make sense of it. This is a P cubed, this is P to the 1st, which is really this P to the 4th that we started with. We have not changed our values at all. What about Q to the 14th, Jordan? What should I break that into?
Q2 as well.
And?
Q2
Very good. Why 12 and 2? Why 12 and 2?
12 plus 2.
Very good. 12 and this 2 is what gives you the Q to the 14. And isn't 12 divisible by 3?
Yeah.
So what am I searching for? I'm searching for a multiple of my index. What are the multiples of 3? 3, 6, 9, 12, 15, etc., etc. I want to find a multiple of 3 that is less than my exponent, but it's biggest at the same time. I want to maximize that multiple. So I want Q to the 12, because I could have made this, really, I could have made this Q to the 9th and make that Q to the 5th, because 9 plus 5 is still 14. But then the Q to the 5th can be broken up into Q to the 3rd and Q to the 2nd. Okay, again, I can change these numbers, but it's not going to help me too much. At this point in time, just reduce. The cube root of 27 is just 3, because 3 times 3 times 3 is 27. Then I just do my rule. I divide my exponent by my index. P, what do you get? Good. Q to the 4. Again, how do I get that? 3 divided by that 3 is where this 1 really comes in. 12 divided by my index is where this 4 comes into play. And then I write what's left over. Okay, and again, I don't need the 1 for my P exponent, so I'm going to get rid of it just so we're clear about that. You're not going to see a 1. I can do it. There it is. And there's your final answer. Okay, in radical form. In radical form. So the whole idea is that we're breaking up whatever's inside the radical into different components. Okay, into its different components. Rose.
Can you choose the way you want to solve this?
Like as far as distributing to start or going to radical? Sure, I would make that choice though based on my possible multiple choice answers. If my multiple choice answers all look like this, then I would choose this method. If my multiple choice answers, the answer for this one would be, that's what it would look like if we just distributed, right? If I just distributed this 1/3 to everything, I would get 4/3, 14/3, and this 27 would become a 3 still. And that's the same answer actually. These are identical. But if my multiple choices look like this with rational exponents, I would choose to distribute. If my multiple choice answers had radicals, I would choose to convert to radical. So it's always up to you to decide that. That's why I'm showing you both methods. Okay? And you can prove that this is the same as this if you were to actually do this. You would get p to the 1/3 here. 1/3 plus 1 is 4/3. You would get q to the 2/3. 2/3 plus 4 is 14/3. Okay, that would go back to that answer as well. So you could always go to here and then convert back. But I would never convert to radical and then convert back to rational. It's a waste of time. Go right from here to here if it's rational. Okay, don't convert and then reconvert. It doesn't make any sense. You're doing extra work. All right, let's take a look at another example. What if we had the 4th root of 16, x to the 7, y to the 3, ab squared to the 3rd. Okay? It looks like it's more complicated because there's a lot more stuff going on here. It doesn't look like it. It looks like it's more complicated here just simply because there's a lot of stuff going on with all my variables. But what do I really want to do to start this kind of a problem, maybe? What's the whole goal again? What was I doing? I have to break it up into what? Of 4. Now, before I do that, though, I don't see anything I can use here. Maybe I want to distribute that first, right? Because PEMDAS tells me to really do the exponent first here. It might help. So let's go ahead and do that. So let's write the beginning part the same way. I'm going to ignore that for a minute. We'll get to that in a sec. And I'm going to write this as a to the 3rd, b to the 6th. Okay? Again, why am I doing that? I'm distributing this 3 to both of these terms here. And the reason I'm doing that is so now I can see, well, what do I have to break up a and b into? What will they be broken up into to make this problem easier for me? Okay, now again, my goal is to break this up into 2 parts. One part which can be reduced, and one part which cannot be reduced. What do I do with the 16? Is that reducible? Is there a 4th root of 16 we know? It's 2, isn't it? So let's put the 16 over here with the reducing part. Now, x to the 7th. X to the 7th, it's either x1, x6, x2, x5, x3, x4, x4, x3, x, and so forth and so on. That's all I can break it up into. Which of those choices should I break up the x into? I would go with this one right here. Why? Because I want to find one of these choices that has an exponent that can be divided by 4. Again, I want to find a choice that, can this be divided by 4? Can this? Until we get to right here, right? Again, it's the only one that can be divided by 4. That's why I'm choosing that as my option. So I put the x to the 4th over here, and I put the x to the 3rd over here. Again, whatever is divisible by the 4 goes on the left side. Whatever is not remains on the right side. Easy enough that way? Next, y to the 3rd. Can I break up y to the 3rd into anything that's divisible by 4?
No.
No, it doesn't work. Try it. 1 and 2. That's it. You're done. Can't break it up into anything else. So y to the 3rd can't be reduced. So let's put it on the right-hand side there. Next, a to the 3rd. Can that be reduced? Be careful. A to the 3rd. You jumped the gun. A to the 3rd cannot be reduced. So I put that over there also. Again, a to the 3rd and y to the 3rd, you can't break them up into anything. You can break them up into y to the second and y to the first, but that doesn't really help me here. Now, I see that I have b to the 6th. What can 6 be broken up into? Good. 4 and 2. It could also be broken up into 5 and 1, right? But does that help me? Because I want to find something that's divisible by 4. So that's not going to help me at all. So 4 and 2 is the spot. So I put the 4 over here, and again I put the 2 over here. All right? So on the right-hand side, am I going to do anything with this stuff? Why not? Yeah, these exponents are not divisible by 4, which is my index. So I can't simplify it pretty much. All right? So this I leave alone. Just write it down, please. And they're almost all cubed. One of them is square. Had they all been cubed, technically, I could have wrote the whole thing with a cube on the outside and left them all alone. If they had all been cubed, right? Imagine this b had been cubed here. Imagine for a second this had been cubed. I could have written this by dropping all these off and just cubing the entire thing. It's the same thing really, right? Just keep that in mind. Okay, it's not in this case, but just keep that in mind. Now, on the left-hand side, what's the 4th root of 16 again? 2. How come again, Marcus? Explain one more time. How come I know the 4th root of 16 is 2?
2 times 2 times 2 times 2.
Is 16. Well done, sir. Again, 4 2's multiplied together are 16. Thus, the 4th root of 16 is just 2. And then I take my exponent and divide it by my index. 4 divided by 4. 4 divided by 4. Okay? And that's my answer. Obviously, without that big space in the middle. Okay, there's really a time symbol here in the middle. Okay, you're not going to see it on the test, though, when you take the SAT. You're not going to see a time symbol there. They're just going to write them one after the other. So the left-hand side is what I can simplify. The right-hand side is what I cannot simplify. Are we clear on this? So what I want you guys to do is see. What is their homework from last night? Can I see the back side of it? You just have it there, right? Like this. All right. On the back side, what I'd like you guys to do is pretty much go through all these problems. But what I recommend you do, and it's completely up to you to do it this way or not. It's completely up to you to do it this way. For this side over here, that's given in rational exponent form, you can convert that to radicals if you start if you'd like to, and then go through this process that you're going to do over here anyway. Okay? You still have about 15 minutes left, guys. You should be able to get through all this almost. Go to the back side, get started. If you want to work with a partner, that's no problem at all. But remember, when you want to make some sample, let's go with homework on. Give yourself a head start right now by looking at number 9 and so forth. Last night you should have done the front side. If you're confused on something, please raise your hand and ask. You don't just sit there, make sure you raise your hand and ask. What's that, 8? Alright. Yeah, remember the end of the class, we did this real quick. Yeah, so we just go ahead and fix it. So, when you were multiplying something, what do you do the exponents? Okay. For example, like, I don't see your work here. Oh, that's that paper. I just see it so we were clear as far as what you did. I don't know what you did. If you want to, you can convert it into radical from the start and make it easier. Or you can start by just distributing the exponents so you can have one. Either way works. Look for number like 26. I just want to go over what you did. Let's talk. How did you get this answer? Where is y in the first time? Oh, I see. You just cancel 5. Okay. When you divide exponents, you have to subtract. For example, if you have this. What does that reduce to? How come? Yeah, so take a look at those problems now. Take a look at the one you did with the 150, right? Aren't those really some exponents? So should you subtract those two exponents? This kind of problem, you want to do 150 minus 2 this. So you're going to get y to the negative 1. You actually have to do. So for example, that's what you have to be doing in the exponent. And 1/5 minus 2/5 is negative 1. Right, that is. Remember in the negative exponent, you make the positive move down the bottom. So for the last two problems, 7 and 8 there, look at your exponents. Distribute wherever you need to distribute first, and then make sure you subtract down. You're going to have to subtract some complicated fractions there. So let's take a look. Like here. B is the second, right? And then it can be the 1/3. So if you're dividing, you have to subtract the 2 minus 1/3. Oh. A was the exponent. What's the exponent here? So 1 minus 1/2 yeah. And you're gonna have some fractions there, so you have to make sure that you might have to do some work on the side. This one has to have the same denominator, so it's easy to get the answer. But if this was like 1/5 minus 2/3, the common denominator, you gotta go through those steps. Okay? Yep. One second, I'm getting ready to. Well, I don't like this example. Okay, well, what's 6 to the 3? That's x squared, right? You don't know what the cube root of 1/3 of 6 to the 4 is. How would I write this as round?
So this will be full speed.
Anybody else have a homework for me for the last two that wants to turn it in, so I can check them at least, before you come for makeups? Just for a heads up on the homework, I'm mostly checking for completion. A lot of the time I pick certain problems to actually go through the answers to. So I'm not going to correct every single one of them, but if I notice like a disparity somewhere, I'll make sure to point it out. You're writing down, you gotta write it down. See, I like the index when I write them before, single before carrying up there. You have a tendency to write like actual big numbers there, which looks like a whole. It's very different there. So like I'm here, like you're 5 there, okay? So looks
I
like
didn't
5
know.
times the square root. Just so you're clear.
I didn't want to.
I'm not gonna correct all of them on here, but just so you're clear.
Oh my God. I just like no, I'm gonna see.
Can you have a negative exponent? Sure, why not? I mean, if you have one though, you have to remember what a negative exponent actually means. What's your name on this, please? What's that? And I mean, I might not need the great word. You know what I mean? Next time I hand them in, it might take some years to It's right there, Rose. Yep. Did you give me homework a little while ago? Somebody else gave me homework in the smart beginning of class. No one else? Not who's homework? I think I have. No, I would evaluate this one here is rational. This is rational. So there's no number. It's just pure numbers. I'm just trying to make the correct. Same process we just did, but now you're working about, same process. Should have probably stopped recording a while ago, right?